All right, I was muted. Anyway, so hi everyone. Um, am I audible now? Just give a yes in the chat if I'm audible. Or is my voice too loud or too low? Or is it fine? Okay, so let's begin now. All right, so hi everyone. Welcome to today's Leetcode PCD of today's contest, biweekly contest, and we'll discuss all the problems from A to D. And before starting that, I will tell you about our self-paced courses. Okay, so if you are someone who is stuck at just solving um, like one or two problems per contest, then our self-paced courses is exactly what you need. We have structured the program into 4 levels so that you can start from wherever you are: beginner, pre-intermediate, intermediate, or advanced. You will learn the most relevant CP concepts through recorded video lectures by educators, followed by carefully curated practice problems, combined with guided hints and detailed video solutions that help you understand the why and not just the how. We believe in helping you build real intuition. If you need more help, you will get instant doubt support from high rated mentors, so you are never left stuck. And beyond learning, you can enjoy leaderboards, gamified progress tracking, internal contests, and PCDs to keep you motivated and consistent. Pick the level that fits your goals and start learning today. And if you are not sure that which level you should you pick, then you can watch this video, and also you can watch the particular level's course video, and you can even see the topics that are listed right here. All right, so let's begin now. So today our first problem was this one. It was called maximize y sum by picking a triplet of distinct x values. You are given two integer arrays x and y, each of length n. You must choose three distinct indices I, j, and k, such that all three x values are unequal, they are distinct. Your goal is to maximize the value of yi plus yj plus yk under these conditions. Return the maximum possible value that can be obtained by choosing these indices. If none exist, then return -1. Okay. So what they are saying is that we have one array of we have one array of x and one array of y. So we have been given two arrays. Let's take a sample only. So let's say we have 1 2 1 3 2, 1 2 1 3 2, and for y we have uh, wait a minute. All right. So yeah, we have this thing right here. We For y we have, where did it go? Okay, here it is. So for y we have 5 3 4 6 2. Okay, and so okay, what we are wanting to do is we can choose any three indices I, j, and k so that they are distinct. They are distinct, and also the x value of xi, xj, and xk are also distinct. Like xi, xj, and xk, they are also distinct. We have to choose three indices I, j, and k such that they are distinct. So for example, we can choose like this index, and this index, because these three are distinct. Or we can choose maybe this, and this, because these three are distinct. But we cannot choose these three indices, because even though the indices are distinct, the value of x is not distinct for them. Okay. So yeah, we can choose any three distinct indices, and we have to maximize the value of the corresponding y, right? So yi plus yj plus yk, right? Now how to solve, like let's say for this sample we want to find the answer. So what is the answer? Now, okay, in this we have only three different x coordinates, right? We have only three different x values, 1, 2, and 3. So if we want to choose three distinct values, definitely it will be 1, 2, and 3 only, right? What we have chosen. Okay. So definitely you will choose a 1, a 2, and a 3. So which one will you choose? Like, will you choose this one or will you choose this one? So definitely you will choose this one, because the value of y for this one is 5 and the value of y for this one is 4. So definitely you will choose this one, right? Then for this 2, like you will have to choose a one, like have to choose a 2. So which 2 will you choose? So for this 2 the value of y is 3, and for this 2 the value of y is 2. So you definitely will choose this 2, right? And what about 3? So there's only one 3, so you'll have to choose this 3. So if you choose this, you will choose a 6. So you have chosen 5, 3, and 6 from y. So the answer is 14, and 14 is the maximum possible if you want to choose three distinct. All right. So as you can see, the output is 14 in this case, right? So therefore, the answer of the sample is 14. So now, how do you actually solve this in generalized case? So first of all, let's talk about the intuition. Like actually, we can get the intuition from a sample itself. Like what we did in a sample, we can just do in general as well. Like our intuition is basically that we want to select three different x's, right? And for each x, whatever we choose, like for some xi, see, let's say here if I wanted to choose one, so with one, what is the maximum? Either I can choose 5 or 4. So definitely I'll choose 5. So for each xi, for each value of x, I will find out the maximum value of y. Okay, and then I will just choose the maximum three of them, right? That's it. Like simply what I'll do is that, let's say, even if our array had more than three distinct x values, like here we had only three x values, right? 1, 2, and 3. So we knew that we had to choose 1, 2, and 3 x values. So we just saw that which one should we take from 1 and which one should we take from 2, and the 3, only one 3 is there. So we saw that. But what if there are more than 3 x values? So we have an option now. So let's say we have um, 5 x values or something. 1, 2, 3, 4, 4, 5, 5. So we have 7 elements and it has 5 distinct values, right? And the corresponding y is given to be, let's say, something like 2, 3, 1, 5, 6, 7, and 8, something like that. So now, out of like these 5 values of x, which 3 will you choose? Which 3 will you choose? You will choose those 3 in which you are getting the highest value of y, right? So let's say if I just keep track of what, like if I choose x equal to 1, then what is the highest y I can get? So if I choose x equal to 1, the only y is 2, right? So I can get y equal to 2. If I choose x equal to 2, then the highest value of y I can get is 3. So y is equal to 3 I can get. If I choose x equal to 3, then the highest value I can get is 1. And if I choose x equals to 4, then the highest value will be 6, because with 4 I have 5 also and 6 also. And with x equal to 5, the highest value that I will have, I can choose from y is 8 for x equal to 5. So simply we have to choose three values from this, and we want to maximize the sum of them, right? Sum is maximized. So what will you choose? You will choose the maximum three values, right? You will choose the maximum three values. So 8, 6, and 3, let's say 8, 6, and 3, and the answer is 17 for this case, right? Like definitely you cannot do directly in this array maximum three values, because it might happen that they have same x. Like here, for example, if you do this and this, these three are the maximum y values, right? So but if you choose this, then these two are same x values, so you cannot do that. So what you will first do is, for each x, you will find out that what is the maximum y that you can choose, right? And then you will just choose the maximum three of them. Okay. And to implement this, you can just, okay, I'll tell you how to implement this, but um, do you get the logic? Someone was not able to solve any problem, so do you get the logic? Sujata, do you understand this? At the red study is saying no. So what did you not understand? Glaring solve this problem using priority queue. I mean, okay, थोड़ा समझ आया. um okay, so I'll just try to explain once more in brief. What you want to do is you want to choose any three indices, I, j, and k, such that the x values are different, right? So essentially you want to just choose three indices like this, such that their x values are different, and you want to maximize the sum of their y. Okay. So let's say that I tell you that you are choosing this 4. Like if you are definitely choosing this 4 as one of your numbers, then which 4 will you choose? Like will you choose this 4 or will you choose this 4? So definitely you will tell me that you will choose this 4 because the y value is 6. And right, and you want the maximum sum of y. So you will choose the maximum y value. So if you want to choose x equal to 4, then the maximum y is 6 that you can get. So for x equal to 4, the maximum value is 6 of y. So for similarly for every value of x, you will just find out that what is the maximum value of y, right? So that is your options. There are options, and you can just choose any three of them. You are allowed to choose any three of them because x is different in all of those options. So you will just choose the maximum three. So you will choose 3, 6, and 8. I mean for y. So essentially, what you are doing is you are chosen this index, and this index. Okay. Custom comparator, um, unordered map. Like I don't know. Like okay, you yeah, that's what I did. This is what I did. Used hash map for x to y. Like what I did to implement this, I'll just show you the code. So what I have here is I have a map, or we can only have it as hash map as well. So unordered map int to int m. Okay, and so what I did was I just stored the maximum value for every value of x. So I just iterated on this array, like on both the arrays, and I just stored that what is the maximum value of y corresponding to a particular x. So m of xi equals to max of m of xi comma yi. So like we are iterating through this I equal to 0 to x dot size minus 1. So for the current xi yi, so this yi can be a maximum value for the current xi. So I am just taking the max with m of xi. So m of xi is equal to max of m of xi comma yi. Okay. And now I just stored all of these um, variables, like all of the pairs in this map, into a vector of pair. And I stored y first and then x. Like I just stored y comma x pairs. Okay. So let's say um, this was the this was my array. Then I just stored in a vector like 2 comma 1, Then I stored 3 comma 2, like basically y comma x. Okay, 2 comma 1, 3 comma 2, and so on, and 1 comma 3, and 6 comma 4, and 8 comma 5, right? And in this, I want the maximum y values, like the maximum value of y. And since the y is the first pair, first element, I can just reverse sort this. So like I reverse sorted this. So it is 8 5, 6 4, 3 2, 2 1, and 1 3, right? And I just took the highest y values, right? And now I realize this, that I don't need to even push back the pairs. Like I don't need the value of x, right? I can just push back the e dots, the y value, not the x value. Like I don't need the x value, right? I'm just finding out the sum of first three elements. So I can just push the y values. So let's do that now. Vector of int v dot pushback e dot second, and then I just sort it. I reverse sort this array, and yeah, if v dot is less than 3, that means that there are not enough x values. Like if the number of x values in my given array is less than 3, then we have to print -1, right? So I returned -1 in that case. Otherwise I'll just return v0 plus v1 plus v2, like the three highest elements ka sum, right? This is your entire code. So this should work. All right. Yeah, it is accepted. So now, okay, do you all get the code? If you have a doubt in the code, then you can ask me right now. Here is the code. Any doubts you can ask. Okay, let's go to problem 2 now. Best time to buy and sell stock 5. So this is the fifth version of this problem. Okay. You are given an integer array prices where prices I is the price of a stock in dollars on the ith day and an integer k. You are allowed to make at most k transactions where each transaction can be either of the following: normal transaction, that is buy on day I and then sell on a later day j, where I is less than j. Sorry. You profit prices j minus prices I. Or we can do a short sell transaction, sell on day I, then buy back on a later day j, where I is less than j. You profit prices I minus prices j. Note that you must complete each transaction before starting another. Additionally, you cannot buy or sell on the same day you are selling or buying back as a part of the previous transaction. Return the maximum total profit that you can earn by making at most k transactions. Okay. So the problem actually says that what we have here is a list of stock prices. Okay. So let's take a sample: 17982, 17982, right? So, and here k is equal to 2 is given. So what they're saying to us is that we can do at most two transactions, like one buy and one sell counts as one transaction total. Okay, like one buy plus one sell is one transaction, whole transaction. All right. So in this case, we can do either 4 buy sells. Like we have to do 2 buys and 2 sells. Okay, like in the maximum case. All right. So what we can do is we can do at most 2 transactions, and transaction is meant by, like, on any day I, you can buy or sell, and on a later day j, you can sell or buy. So this means that on the day I, if you bought, then on day j you will sell, and vice versa. Like you cannot do something like, let's say you bought the here. So like you bought one stock on this day, then you bought one stock on this day. You cannot do this. It is not allowed. So what you can do is, you can buy here, let's say. Then let's say here you don't do anything. Then here you sell it, right? So the profit that you gained is 8. Okay. And then let's say here you buy again, or not, sorry, you sell. I mean, you sell for 8. So you sell for 8, and here you buy back for 2. So here you got the profit of 6. So total you made 2 trades, and total you got a profit of 14. Okay. But it is not allowed that you buy and buy again. Like it is not allowed that you buy here and then buy again here, and then sell here and then sell here. So even though you have bought and sold 2 times, you cannot do this, because if you have bought once, then you must sell after that. Okay. All right. So this is the problem, that you have to find out the maximum profit that you can make using this scheme. Okay. So for this case, optimal way, I think you should see that you can buy for 1 rupee and the sell for 9, then you can sell for 8 and then buy for 2. So essentially you bought for 1, so -1 here, then you sold for 9, so +9, then +8 and -2. So total profit would be 8 plus 6, 14, right? And the answer is 14. Okay. Yeah, so this is the problem, and we can solve this. So okay, we'll solve this right now. Actually, what here we can observe is, okay. All right. So first, let us discuss intuition. Intuition here is basically that we can either buy, okay, like on each day, we can either buy or sell, or we can do nothing. Like either we can buy or sell, or we can do nothing on some day. Like on each day, we have 3 options: buy, sell, or do nothing. Okay, right? But there is one more condition, that let's say that here I did nothing, then here I bought. Then what can I do here? What can I do here? I can only sell or do nothing. Like I cannot buy. Buying is not allowed. Either I can sell or do nothing. N means nothing. Okay, right? So let's say I just did nothing here. So N. Okay. So here what can I do? I can sell only, like sell or do nothing, because I have currently a bought. I have currently bought something, so I can either sell or do nothing, right? So this is what I mean. And let's say I sell here. Let's say I sell here. So at this point, I have 3 options, like buy or sell or do nothing, right? So basically, what I can do on the current move, like on this day, what I can do actually depends on what I have done previously. Like if I have bought previously, then I can not buy here. Buying is not an option here. So basically, it depends on what I have done previously, right? But actually, at most three options can be there for each position. Like for every position, at most three options are there, that either buy or sell or do nothing. So it is quite similar to a knapsack. Like in knapsack, what we have is that we can take or we don't take, right? Or like for every index, we can either take or we can not take, like either take or don't take, right? So for every index, we have take or not take, and take or not take. But the difference is that in normal knapsack, they are independent. Like whether or not, like whether I have taken or not here doesn't affect that can I take or not here. Okay. But here, if I have bought, let's say, then I cannot buy again right here, right? So it affects. So the thing is that we have one more, like more conditions to take care of. But more or less, it is knapsack only. Like in knapsack, you have take or not take, two options. And in this thing, you have three options: either buy, or you can sell, or you can do nothing. So we can just try to build upon the knapsack intuition. Okay. So how do we solve knapsack? Like let's say we want to find out, we have the weights here, W1, W2, W3, W4, W5, W6, and W7, and the V1 up to V7. So yeah, what we used to define is dp of W, or dp of I comma W, is the maximum value we can get if we take exactly W weight from the first I indices. Like if I is equal to 4, then from W1 to W4, how much can I actually get the value if I take exact W space, W weight, I mean, right? So in our profit thing, like in our profit and loss scenario, what we can actually take is, okay, let's do it recursively. Like this is the iterative approach that I talked about. What about recursively? If you want to solve recursively, that is, if you want to solve the answer, the maximum value, for, like let's say 0 comma capital W, that is 0 comma total weight that you have. That means considering the array from 0 to n minus 1, what is the maximum answer? That is the value of 0 comma W, right? So you do that, either you take, so it is maximum of, either you take the first element, so um, V1 plus, I mean, let's say 1 comma W. So value of 1 comma W is maximum of V1 plus value of 2 comma W minus W1, or you don't take, so it would be value of 2 comma W, right? This is what you do in knapsack. So in your this problem, what you can try to do is a function define a function which will return you that what is the amount of money you have earned, like money you have earned. And its parameters will be, like, of course, the index. So here we had the index 1, denoting that the answer from 1 to n minus 1, or 1 to n, right? So here one parameter is the index, that money earned is I from I to n, if I consider. All right. Then one more parameter that we can take here is that how many trades we have already done. Like here, this is the weight, right? In knapsack, this parameter is index and this is weight, that how much weight do we currently have. So in this case, what I can store here as J is basically the number of trades that I have done, right? And in this case we will also take one more parameter, that is our current, like have we bought or have we sold or have we not done anything. Like, see, let's say money earned of ij comma k, let's say this is k. So this denotes that if I have, like, if I'm considering the stocks from the ith day to last day, okay, if I'm considering these days, and I can make j trades. Wait, what I have taken in my solution, let me just check that. Okay, yeah, so um, j is basically that how many trades do I have left, like how many more trades can I do in this I to j, like how many more trades can I do. Like in knapsack what we have is how much weight can we take more as one of the parameter. So in this case we'll have as a parameter that how many more trades can I do. Okay, and the third thing is that whether I need to buy or I need to sell or whether I can do anything. Like, see, I'll take an example. Let's say, let's just take this example, 17982, right? So we want to find the answer to this. So basically what we want is we want the answer of 0, like this is 0 1 2 3 4. So we want the answer considering all of the elements, that is from 0 to 4, and we can do at most two trades, like, or two transactions. And like here it is n, so n means we can do anything. On the next move we can do anything. All right, so what is this equal to? Like on the first, if it is n, then we have three options, right? We have three options that either we can, wait, so okay, we are at the day 0 right now, right? So either we can buy on the day 0, right? So if we buy on the day 0 it will cost us 1. Okay, so the money that we earned is -1, and we can add the answer of 1 1 comma s. So what I have done here is that if I buy on the day 1, that means I'll have to sell on the next day, right? I mean on the future day I'll have to sell. Okay, so whatever is the maximum amount I can earn from that, -1, that is my answer to this. Like there is one possible value. And if I choose to sell on the day 1, if I sell on the day 1, then it is just 1 plus answer of 1 1 and sell. And if I do nothing, then it is just answer of 1 2 and n. Like, I hope I am being somewhat clear. Like what I have just done is I have defined three states. One state is the index. One state is the number of transactions that we are left, that we can do. And this state is that what can we do. Like n means that we can buy, sell, and do nothing. And s means that we have to buy on the next step. Like since, sorry, s means we have to sell on the next step. Since we have just bought right now, that means we have to sell later. That's why we are calling this answer with s. Right, and if I have sold, sorry, here should be b. If I have sold today, then I have to sell at the next day. So 1 plus answer of 1 1 b. And if I do nothing, then it is just answer of 1 2 n. Like if you saw, like in the knapsack what we have the value from for 0 comma w, is basically the maximum if we buy, like sorry, if we just take this value, so v0 plus value of 1 comma w minus w0, or um, value of 1 comma w. So you have two options and you have to take the maximum one in the knapsack. So similarly in this case we have three options that either we can buy. So in that case we'll go to this state, answer of 1 1s, or we can sell on the first move, so we'll go to this state, and or we can do nothing, so we go to this state. So now let's say we have gone to the first state and we want to, so now what we can do, like we want to find out the answer of 1 1s. So 1 1s means that okay, at this point we have to sell or we can do nothing. Like we have two options, either we can sell or we can do nothing. So if we sell, then it is basically this 7. So 7 plus answer of 2 comma 1 comma nothing. Like see, here we did one buy and we did one sell. So now again we don't have to do anything, like there's no compulsion. So this answer is either 7 plus ans of 2 1n, or if we do nothing, then that means we'll have to do answer of 2 1 sorry, yeah, 2 1s. That means if we don't sell right now, we have to sell in the future. Whatever, whenever we do something, we have to sell. So either we can sell or do nothing. So similarly you can make this tree, like this tree will be formed and you can solve it using the DP approach. So basically this is what you can simply do, that your answer of ij k is basically I is your index and j is your number of trades that you can do, and k is like the maximum, sorry, k can be either buy or it can be sell or it can be do nothing. So if it is buy, then that means you have to buy or do nothing. If it is sell, that means you have to sell or do nothing. And if it is nothing, then you can do anything. You can either pass or you can buy or you can sell. That is your thing. So that's why I have three states and we can do transitions like this. And actually, instead of that, what I have done is I have just multiplied this k by 2. Like in my input, if I get k as 2, like let's say I get k as 2 in my input, then I will take k equal to 4. I'll start from 4, and at each step I will decrement my k, because see, if k is equal to 2, that means you are buying, like you are doing two buys and two sells. So essentially you are doing four transactions, right? That's why I am multiplying my k by 2. So I'm starting this k as 4. So every time I transaction, I reduce this k. So 3, 3 and 3. Sorry, not 2. Like here it is 2 only. And here if I sell, then it is once more reduced. So it becomes 2. And here it remains as 3 because I did nothing. All right. So this is your entire state diagram, like your tree, which you can make and get the intuition of why we chosen, like why we chose this states. And the base case is when we have like reached the end. So if this is your array of your prices and you have reached the end, then that means your answer is equal to 0. If you have some orders left, like if you have no positions left, let's say let's take a simple case. Let's say we have 1 and 2 as our prices and our k equals to 1. Okay, so let's say we have three options here: buy or sell or do nothing, right? If we are at position number 0, for example. So if we are at the state, 0, 2, comma nothing. So we have three options: either we can buy, or we can sell, or we can do nothing, right? So if we buy, we'll go to the state of 1 comma 1 comma sell. That is, we have to sell now. Then, or if we sell, then we'll go to the case of 1 comma 1 comma buy. And if we do nothing, then we go to the case of 1 comma 2 comma nothing. Now, for example, from here, if we go to let's say we sell, like we have two options right here: either we can sell or we can do nothing. So if we sell, then we go to 2 comma 0 comma n, right? Like we bought once and then we sold once. So now we have reached this n state where we can just do anything. And if we did not buy anything, like we did not buy in this case, then we will remain at 2 comma 1 comma s, right? So this state is not valid. Like the answer for this state is like you you can never reach this state, because you have reached the end of the array, right? This was the index 0, this was the index 1, and you have reached the index 2. That means your entire array is gone. Like you have traversed the entire array, but still you have a cell left. That means you have to sell something. You had bought earlier, but you haven't sold it yet, and you are already at the end. So it is not possible. So you will just return minus infinite here. All right. So this state is not valid, but this state is valid actually, because you have sold everything that you have, and you have no remaining trades also. So in this case, you will return 0, right? So the maximum of these two is 0. So this state will take the value of 0, and since we like sold here, basically 0 plus the value that we get from this. So if we sell it, so we get 2 value. So 0 plus 2, which is 2. Sorry. So, yeah, so the value for this state would just be 2. And then you can just compute the other states as well. But my point was that in the base case, if you have some transactions left, that is, you have to sell something, but you have reached the end, then the answer is minus infinity. Like it is not valid. You cannot do that. And if you have some trades remaining, like let's say here you bought nothing, so you have 1 to n, and again let's say you did not do anything, so now you are at 2 comma 2 comma n. So now, even though you have no positions left, like even though this is valid, but you have some trades left, right? So that's why the answer is minus infinity for this one as well. All right. So the only case where the answer is 0 for your base case is where your j equal to 0 and your k is equal to n. So like you have no current positions right now. That is, whatever you have bought, you have sold, or whatever you have sold, you have bought again. Okay. So this is your base case. So I'll just summarize that your dp of ijk, in this case, like this is the maximum, like maximum money you can earn if you have like considering the index from I to n, or I to n minus 1, using j trades, and such that this k is either buy, sell, or n. So if this k is buy, like if this k is b, this denotes that you must buy or do nothing on the next one, like must buy. That means you already have bought one stock. Sorry, you already sold one stock, and you must buy it again. And s means you have already bought some stock and you must sell it. And n means that you don't have anything on your hands and you can do whatever you want. So I means the answer from I to n, and j means the number of trades that is remaining. All right. So the transitions are very simple. Like if you are at the current state ijn, then you can either buy, or you can sell, or you can do nothing. So if you buy, you will go to I plus 1, um, j minus 1, comma, sell. That is, if you bought, then you will have to sell next. And if you bought right now, then it is I plus 1, j minus 1, and buy. And if you do nothing, then it is I plus 1 and j and nothing. All right. And you can simply just solve this and get your answer. Like, it is pretty simple. So the recursive DP is pretty simple. I'll just show the code for that. Like here, I have this n equal to prices dot size. I just initialize this n, and I'll multiply k by 2. This is equivalent to multiplying this k by 2, because I am left shifting it, right? So I'm multiplying it by 2 essentially, and I'm initializing my DP with L long minimum, right? Like all of my DP values I'm initializing with L long min. And also I have made a prices vector here so that I can access it from my answer array. So I am initializing that. This prices is equal to prices. So this prices is assigned to this prices right here. Now, final answer. Like, to find the final answer, I am calling this answer variable from the index 0, starting with some trades, like from 0 to k, and it is n. Like here, 0 means completed, that means n. 1 means bought, like to buy, and 2 means to sell. To buy and 2 means to sell. Okay. So I am just calling this answer function for every value of j, that is the amount of trades that we can do. Because in the problem, they have said that we can do at most k transactions. Like, they haven't said that we have to make exactly k transactions. We can do at most k transactions. So we can go, do anywhere from 0 to k. So I'm just iterating over this from 0 to k. If I do these many transactions, what is my maximum answer? And I return it. So in my answer, I just have this recursive code. Okay, so first I have this base case. The base case is that if I reach the end, if I equals to prices dot size, then if j means if j is not equal to 0, that means we are left with some transaction that we could have done. Then we return infinity. Like, that is, sorry, we return minus infinity. That is, we cannot do this. Like, we have reached an invalid state because we haven't exhausted all of our operations yet. Now if k, that means if k is not equal to 0, that means if k is not equal to n, like if we have not completed anything, then we'll return also minus infinity, because we have to complete the transactions. Like, if we have bought, then you have to sell in the future. Otherwise we return 0. Like, if these both are 0, then we return 0, because it is a fair trade. It is a it is a valid final state. All right. So this is the base case. Then we have the memoization. In my memoization, I have, if dp of ijk is not equal to the minus infinity, I return dp of ijk, because I had initialized it here to L long min, right? Then if these two are false, like if I did not return here, that means I'll have to calculate. So I have two cases, that if my state is n, or if my state is not n. Like, let's say, sorry, if my state is not n, then either we can not do anything, we can do nothing, right? So ans 1 is ans of I plus 1 comma j comma k, one possibility. Or we do something, like whatever we can do, we do. Like, if k equals to 1, then we have to buy, right? K equals to 1 means we have to buy. So we buy. So it is the so ans 2 is the answer of I plus 1 comma j minus 1 comma 0 minus prices of I, because we have bought it. So I'll subtract my value, and if k is 2, then I have to sell. Like if I sell right now, then my ans2 is ans of I plus 1 j minus 1 comma 0 plus prices of I. So we have two options: either we don't do anything, or we do that thing which we have to do, buy or sell. And whatever is the maximum, we will save that value and return it. Right. So this was the case when k is not 0. K is not 0 means it is not n. And if it is n, then we can buy or sell, or we can do nothing. So let's say we do nothing, then it is stored in ans1. And ans2 is basically if we buy. So ans2 is ans of I plus 1 j minus 1 comma 2. So comma 2 means that we have to sell in the future. Like since here we are buying at this step, we have to sell in the future. So this 2 means we have to sell. And minus prices of I because I'm buying. And ans3 is the answer I plus 1 j minus 1 comma 1 plus prices of I. And I'll return the maximum of ans1, ans2, and ans3. And also I'll store it in my DP of ijk. Okay, Vish is asking why did multiply k by 2? So just see here. Like let's say we have just 2 days, 1 comma 2, and here k is given to be 1. So in my question, one trade is defined as one buy and one sell. Like one buy and one sell is defined as one transaction. So if k is 1, then they are saying that I can buy once and I can sell once. So basically I can do two operations. Okay. And since in my function my j parameter is that my j parameter is basically j is how many operations can I do. So that's why I multiply k by 2. So for example, here we start from, like if we have 1 comma 2 as this array, then we start from this state 0 comma 2 comma n. So we can do anything. Now either we can buy or we can sell or we can do nothing. So if we buy, that means we have done one operation and we go ahead. So one operation and we have to sell now. And if we have sold right now, then it is 1 comma 1 comma buy. And if we did nothing, then it is 1 comma 2 comma nothing. So since I am like decrementing this j every time I am buying or selling, I have to multiply it by 2 also, because in the question the k is like 1k means one buy and one sell, but I am decrementing it after every buy and after every sell. So I have to multiply it by 2. Okay, so Yash is asking that why do we need to run a loop for all values of k? Actually, Yash, the reason is that I have defined my answer to be in that way. Like my answer of ijk is basically that if I do exactly j operations, if I do exactly how many operations, like my answer of ijk is basically if I do exactly j operations from I to n, then it will return that. And if I cannot do in like those operations, then it will return infinite minus infinity. Okay, so like that's why we need to do I did from all 0 to k. Like here, what they're asking, we want the maximum profit that you can earn by making at most k transactions. And my answer actually returns that how much profit can I gain if I do exactly j transactions or operations, if I must. So since this is exact, and here we have to do at most k transactions. So like we can do anywhere from 1 to up to k transactions. So that's why we have to iterate all from 0 to k. Or actually, more accurate will be plus equals to 2. Like I equal to 0, I less than equal to k, I plus equals to 2. Because definitely we won't do any odd operations, right? Like we have to buy the same number of times that we sell. So odd number of I will not work definitely. So we can just do this. All right. So I hope you understood this DP problem. It was similar to knapsack very much, but except the fact that what moves we could do was dependent on what we had done previously. So we have, if we have any open positions, then we could not buy another one, or if we are short a stock, then we cannot sell another one, right? So we just stored that as a state, that are we short any stock, or are we long any stock, or are we neutral? All right. So yeah, I think it should be clear by now, and the code also should be clear. Like essentially, I just have two cases or three cases essentially: k equal to 1, k equal to 2, or k equal to 0. So if k equal to 0, then we can either not do anything, or we can buy, or we can sell, and we just take the maximum of three answers. Or if we have k equal to 1, that means we have to buy, or we can do nothing. And if we have k equal to 2, then we can sell, or we can do nothing, right? So we just take the maximum of both the answers. And yeah, complexity. So um, in this case, my DP has n into k into three states, right? Like what I have is, I have three states: the index, the j, and the k. So index can be from 0 to n, and j can be from like 0 to k, where k is in the input, and this is from like 0, 1, or 2. So basically I have 3 into n into k states, right? And the time transition is just O of 1, because from one state I have either three choices or two choices. So it will take me either two time or three time. That is O of one time it will take. So the time complexity is O of n into k. And here n and k are given to be like, this is n is up to 10 to the power 3, and k is up to n by 2. So this will work. Yeah, like 2k. So you can say 6nk states, because I multiplied k by 2, right? So it can be from 0 to 2k. ओ ऑफ के स्पेस में कैसे करे लेने लिया है? What? I think you are asking how can we do O of k space. We have in fact done O of n into k space. Or are you asking that how do we solve it in O of k space? Is that what you are asking? Like, Manoj, what are you asking? I don't get it. Okay, so you are asking that how do we solve it in O of k space? That is a good question. That actually we can do it in O of k space as well, because as you can see that my answer for ijk only depends on the answer on I plus 1 and something. So I plus 1 jk, I plus 1 j minus 1 0. So actually, instead of just storing the entire table, like what we are storing is for every n, like for every index and for every j, we are storing, or I'll write I here. Okay. So for every index and every j, we are storing the answer. But actually, we don't need to do that, because um so 0, 1, 2, 3, 4. So let's say we are storing, like let's say we want to calculate this answer, then it is dependent on only the I plus 1th row, right? So when we are calculating RDP, we can simply iterate from the back and just store the last row that we have calculated. So we would have to just store this row and this row that we are calculating right now. Like we will store this row, and we will store the new answers in this row of this row, and then we will just delete this row, like the answer of this row, and we'll use this row to calculate the answers for this row. So like actually O of k space O of k space is only possible in iterative DP. If you do iterative DP, then only it is possible. In recursive, it is not possible. Ankur Rai is saying main function has a loop of transactions. Yes, it has. So if you are doing iterative DP, then you would not call the answer function, but you would just use DP of ij, like 0, comma I, comma 0. If you did iterative DP, then you would not call this function because you would have no function. So in that case, you can do it in O of k space also. All right. So any more doubts in this? Okay. So I'm assuming no doubts. All right. So let us move on to the next one. Maximize subarray GCD score. You are given an array of positive integers nums and an integer k. You can perform at most k operations. In each operation, you can choose one element in the array and double its value. Each element can be doubled at most once. The score of a contiguous subarray is defined as the product of its length and the GCD of all its elements. Your task is to return the maximum score that can be achieved by selecting a contiguous subarray from the modified array. Note, a subarray is a contiguous sequence of elements within an array, and GCD is the GCD. You know what GCD is. So, what we have to do, what they have told us is we have been given an array. Let's say A1, A2, A3, up to AN, right? And what we have to do is we have to maximize the score of a subarray, and the score of subarray is defined by the GCD. Like let's say the subarray is from L to R, so it is defined as the GCD of AL plus 1 up to AR multiplied by the length of this. So this is our score, right? And we want the maximum score that we can have. But before that, we can do k operations. Okay. So we can do at most k operations. And in one operation, you can choose any element and double its value. But you can double each element at most once. All right. So let us look at this test case for now. Let's say we have 2 comma 4 and k equal to 1. Okay. So you have 2 comma 4 and k equal to 1. So k equal to 1 means you can double any element at most once. So you can double at most one element. So let's say you double this 2. So the array will become 4 comma 4, right? And now you take the subarray from L equal to 1 to R equal to 2. That means the whole array you take as a subarray. So the score of this is what? The score of this is GCD of 4 comma 4 into the length, which is 2. So the answer is 8. And this 8 is the maximum score that you can get. All right. And let's say for this one, we have 3, 5, 7 and k is 2. So we have 3, 5 and 7 and k equals to 2. So what we can do here is we can multiply this. Okay, what we can do, like we can do at most 2 operations. But what I'm telling you is just double this thing, like double this 7. So it make it 14. Okay. And then choose a subarray from L equal to 3 to R equal to 3. So the subarray is just 14. And the score is GCD of 14, which is just 14, multiplied by length, which is 1. So the answer is 14. And that is the maximum that you can get. All right. And in this case, the output is 15. because you can multiply any element by 2, but that won't have any benefit. Okay, so maximum score is 15. So yeah, you have to just do that. You have A1 to AL, A1 A2 to AL, and you have to figure out the maximum score of a subarray. I mean AN, not AL. To AN, you have. Okay. So guys, what can you do? Just let's just think about it. So one thing that we can think is what are the constraints. So the constraints here are that n is up to 1500 only. N is less than equal to 1500. Okay. So that means that we can do O of n square solutions. Okay. So let us think about that. So O of n square means we can simply iterate over all subarrays. Like we can simply iterate from L equal to 1 to n, and from R equal to L to n. And then we can check that if I want the answer of L to R, like if I want that this subarray is my maximum, like what can be the maximum possible, what they have called score, what is the maximum score for this subarray. So if you just iterate over the all subarrays and find the maximum score for this subarray, then you can simply find out that what is your optimal answer. Like you just take the maximum of all. You will just take the maximum of all the answers. So for example, we have let's say I'll take my own example, 2, 4, and 6, and your k is equal to 1 in this case. So what you will do is you will iterate over all subarrays. So let's say you iterate over all subarrays, let's say 2. So what can you do in this case? You can multiply this 2 by 2 once more, right? You have k equal to 1. That means you can multiply this 2 by 2. So it will become 4. And the answer is 4 for this. 4 into 1, which is 4. And if you take 2 comma 4 subarray, then you can multiply this 2 by 2. So it will become 4 comma 4. And the answer for this is 8. Then you will check the subarray 2, 4, 6. And um, you can multiply this 2 by 2. So you get 4, 4, and 6. And the GCD is what? 2. So 2 into 3, answer is 6. And so on, you will just check for all subarrays and you can find out the maximum possible answer. Right. And I think the maximum answer would come when you have this 4 comma 6 and you multiply this 6 by 2. So it becomes 4 comma 12. And yeah, so it will give 4 into 2, which is 8. So I think it is the answer here, unless I am mistaken. But anyways, so that's what we are trying to do. That just iterate over all subarrays and just check that what is the maximum value that you can get. But how do you actually check for a subarray that how much score can it be? Like see, if we were not to do the operations, like let's say we did not have to do the operations, that we can double any element at most once. So if we can, like if we did not have those operations, then our answer is just r minus l plus 1 multiplied by the GCD of al al plus 1 up to ar, right? That is the answer. But since here we have to do the operations, what how do we determine that? What do we do? Like let's say we have this subarray. Current subarray is 2 comma 4 comma 12, for example. So to maximize the GCD for this, like okay, this length is fixed, right? Like whatever you multiply, like let's say we have k equal to 2. So whatever we multiply the elements like by 2, the length will not change, right? So all we can change is the GCD. We can increase GCD by multiplying some elements by 2. So now let's go back to our first class or our third or fifth class and just think about what is GCD. What is GCD? GCD is just Like, how do you find GCD basically? What you will do is just prime factorize all of the numbers and take the minimum power. Like here, 2 is just 2, 2 to the power 1. 2 is 2 to the power 1, and this 4 is 2 to the power 2, and this 12 is basically 3 into 2 to the power 2. So the GCD is what? The GCD power of 2 will be 1. Power of 2 will be 1 because you have the minimum power as 1, and the power of 3 will be 0 because these two don't have a 3. So GCD is 2. But now if you can multiply any two elements by 2, that means you can increase the power of 2 by 1 in any of these elements, right? Then what can you do? You can simply increase the power of this. You can make it to 2. Like you can multiply this one more 2, right? So it will become 2. And in my GCD also it will be 2 because all of these have 2 now. So I have increased my GCD to 4, right? So basically, if we have some array and we are considering it, then we can simply increase its frequency of 2 by 1. Like for every element, we can increase the power of 2, right? So let's say initially in these variables, like let's say 2 to the power p1 was there into some g. Like, see, what I'm doing is in the current subarray, let's say the first element had p1 power of 2, then in second element had p2 power of 2, then third element had p3 power of 2, and fourth element had p4 power of 2, right? So in the GCD, the power of 2 will be what? The minimum of p1, p2, p3, and p4. All right. And what we can do is we can increase this p1, p2, p3, p4 by at most 1, right? Only by 1 we can increase them because we can only multiply 2 at most once to every number. So let's say that this p2 was the minimum. Okay, this p2 was the minimum, and these all were greater. This was greater, this was greater, and this was greater. So if I just increase this mi by 1, like if I multiply this element by 2, then definitely I can say that my GCD increases by double. Like this power increases by 1 if I just give this element a 2. For example, if I have 2 to the power 4, 2 to the power 4, 2 to the power 3, 2 to the power 2, and 2 to the power 3, and if we have k is equal to 2, then here initially the power of 2 is what? 2. In the GCD, the power of 2 is 2, right? But what we can do is we can increase it. We can just give this plus 1, and now every element has at least 3. So now the power of 2 is 3, right? And my point is that we cannot increase it more. Like let's say even if k was 4 right here or something, like if here let's say k was equal to 4, okay, then you might have said that we can increase, like we can give two twos to this one 2 here and 1 2 here, so they all will become 4. But the thing is that you can only give every number only a single 2. So definitely you cannot increase it more than 3. Like if the minimum is 2, if originally it is 2, then you can increase it to at most 3, right? And you can increase it to at most 3 if the number of 2's there are, like if the number of 2's there are less than equal to number of k. Like here we had only a single 2, only a single 2, so we could give it then all like the 2. But let's say we had something like this: 2 to the power 1, 2 to the power 2, 2 to the power 1, and 2 to the power 1, and we had k equals to 2. So here the minimum is 1, right? The minimum is 1, and it is occurring like 3 times. So if you want to increase it, if you want to increase the GCD, then we will have to multiply these 3 elements by 2. But since we have only k equals to 2, then we can only increase any two of them. So definitely we cannot increase the GCD. So in our GCD, the maximum power of 2 can be 1 only, right? So yeah, that is the entire logic, that if you have any subarray A1, A2, A3 up to AN, then your GCD of this subarray will be just the GCD of your entire thing originally, and you can do it at most into 2, and this into 2 will happen if the number of times minimum occurs, the number of times minimum, like number of minimums in the power of 2, if that is less than equal to k, then you can just give all of them a one more factor of 2, and the GCD will multiply by 2. Otherwise the GCD will remain the same, right? So basically now what we have to do is we have to efficiently solve this problem for a given subarray L to R. Like we have this whole entire array from 1 to n, and we want to find out that what is the answer for this L to R. And if we can do that fast, we will just solve it, and we will iterate over all this ln r, and we can have the final answer. So how to actually find out the answer for some subarray quickly? So for that, what we need just two things, right? One thing is the OG GCD, original GCD, right? That's what we need, right? And the second thing that we need is what is the power of 2, power of 2 in the GCD, right? And also third thing that we need is that how many times, like see, power of 2 in GCD means what is the minimum power of 2 in these elements, right? So the third thing that we need is how many times it occurs, how many times the minimum occurs, right? So if the minimum occurs like less than equal to k times, then we can give it one more 2, like we can multiply GCD by 2. So the answer is GCD into 2 into length, obviously. And if it is greater than k, like the number of times the minimum occurs is greater than k, then we cannot multiply it by 2. So in that case, the answer is just GCD into length. So how do we find out these three things? That what is the GCD of a range L to R? Like we want to find out the GCD of some range L to R. And for that, we can simply use a sparse table. Like any range query data structure, either sparse table or segment tree, to find out the GCD in this range of L to R, right? And the power of 2 in the GCD, so that is just the minimum power of 2 among all of these numbers, right? So I just, like what I did was I stored an array which had all the powers of 2 for all the numbers. Like I just made a new array which stored the powers of 2 in all of the numbers, and then I just found out the range minimum in this L to R, like the minimum value from L to R. So, like for that also, I use sparse table. So I use two sparse tables, one for the GCD of L to R and one for the minimum of L to R. And how many times this occurs in the minimum, like how many times that minimum value occurs, that we can just, like when we're iterating, we can just keep track of how many times every power of 2 occurs in a frequency array. We can keep track of that in a frequency array. We can keep track of that. Like when we are iterating from L to iterating over L to R arrays, we will just keep track of what is the frequency of each power of 2. Okay. Krish, do you get this part? Okay, sorry, that was our previous question, I guess. Yes is asking prefix for the prime factors. or like you can do that, but instead of that you can just store a sparse tree or segment tree for GCD. So you can get the GCD on in O of 1. And actually you can, like, actually one more better way to do this is you can simply keep track of GCD every time you are iterating. Like what you can simply do is you can, like, let's say you are iterating from, like, you're iterating for L equal to 1 to n, and for R equal to L to n. So like while you are iterating only na, you can simply update the GCD. Like you don't need actually sparse table. I just realized that. So what you can simply do is that, let's say your L is right here and you start with R right here, right? So whatever element is here, let's say A3. So initially your GCD is A3. Okay. Now you go ahead to A4. Like you go ahead, your R comes to here. So your GCD will get updated to GCD of A3 comma A4. So you can simply take the GCD of the new element that you are coming to, right? That is much simpler than doing this sparse table. And the minimum value also you can keep track of that, or you can simply find the power of 2 in the GCD. You can do anything you want. Like there are many methods. I use sparse table, but you can do this as well. Like when you are iterating for L equal to 1 to n and from R equal to L to n. So when you are iterating this R, when you are just considering this subarray first, then this subarray, then this subarray, you can just update the GCD as you go along, right? And you can also do the frequency as well. So actually I'll just implement this for you guys. I'll implement this problem on the spot. Okay. So you have nums here, and let's make an array. Nums dot size vector of int power of 2. Like, okay. Just pardon my typing. So here what I'm doing is I am calculating the power of 2 in every number, right? So I'm storing it in PO of 2, and then I'll just iterate for int L equals to 0, L less than equal to L less than L, L plus plus, because 0 is indexing. And for basically I'll have long answer equals to 0. Okay, so ans is equal to max of ans comma, like if I just choose this L comma L subarray, the L comma L subarray, that is R equals to L, then the answer would be okay, if k is equal to 0, then the answer would be different. What is the constraint on k? K is from 1 to n, right? So we can multiply it by 2. So if we have this L right here, like for subarray L to L, the answer is 2 into A of L, or nums of L. Okay, and then I iterate for, also I'll int g equal to A nums of L, and int mi equals to PO of I, or PO of L. Now I'll iterate for int r equal to L plus 1, r is less than n, r plus plus, right? And we can simply take g equal to GCD of g comma nums of r, and mi equals to min of mi comma PO of r. And also we need a frequency array. So int fr of 32, fr of PO of L plus plus, and fr of PO of r plus plus, right? So okay, so basically what I'm just doing is currently my mi contains the minimum power of 2 in the range L to R, in this range L to R, and my G is the GCD from L to R. Okay. And also my frequency array contains the powers of 2, the frequency of powers of 2 in the range L to R. And now if my frequency of minimum is less than equal to K, then I can multiply GCD by 2. So the answer equals to max of ans into R minus L plus 1 into G into 2. Otherwise, my answer is just length into GCD. Ans equals to max of ans comma R minus L plus 1 into G, right? And I return the answer. And actually, I cast it into long first. I can overflow. So I'll return the answer. All right. So this is your approach. Okay. Compilation error. Very nice. PO2. Some compile errors. All right. So this is your solution for this problem. I'll just go through it like once again. So what you have here is I'm just keeping track, like for every L to R. What I'm doing is I am keeping track. Why is it shaking like this? Okay, so for some L to R, I'm just keeping track that what is the GCD from L to R and what is the minimum power of 2 in that L to R range, and also what is the frequency of that power of 2. And the if the number of numbers having that power of 2 are less than or equal to k, then I can just increase them all by 1 and the GCD will multiply by 2. Otherwise, I cannot do anything and the GCD will be just GCD. So my score in this case is length into G, and my score in this case is length into G into 2. All right. So I think should be clear. This should be clear. Is it clear, guys? Or do you have any doubt in the logic or the code or something? Guys, just tell me if it is clear. Okay, it's clear. What about other ones? Meanwhile, I'll just show the approach for by sparse table as well. So this is the code for sparse table that I just copied from somewhere. All right, and here's the solution. So similarly, I just made this power array, power 2 array, and I made the sparse table for that. The min sparse table for the power array, and the GCD sparse table for the nums array. And also, this is I'm iterating first over the length and then doing a sliding window something. So this is very poor code. This is I will not show you this. Just assume that this is your solution. Can you walk through your square sparse table code? Uh, this is not what I wrote. Like the sparse table code is not mine. But if you want to learn sparse table, then you can just learn it from some anywhere. Like there are many videos on YouTube where you can learn sparse table. Anyways, so this code must be clear. If till here, like till now, I haven't gotten any doubts, so I'm assuming that it is clear. Okay, guys. All right. So let us go to the next problem, the last problem of today. And this is called maximum good subtree score. You are given an undirected tree rooted at 0 with n nodes numbered from 0 to n minus 1. Each node I has an integer value vals of I, and its parent is given by parent of I. A subset of nodes within the subtree of a node is called good if every digit from 0 to 9 appears at most once in the decimal representation of the value of the selected nodes. The score of a good subset is the sum of the values of its nodes. Define an array max score of length n, where max score u represents the maximum possible sum of values of a good subset of nodes that belong to a subtree, or subtree rooted at node u, including u itself. Return the sum of all values in max score. So basically, what they are telling us to do is we have a tree. Okay. Simply, what we have is we have a tree and some values are written on it. Like, let's say this is a root. This is a root, and there are some nodes, some children of every node. Okay. And on each node, some values are written on that. So let's say here 1 is written, here is 23 written, here is 4 written, here also 2 is written, here 5, 2, let's say 7 and 5, let's say. So basically, what you have to do is from every subtree, like let's say from this subtree, you have to just pick a subset of nodes. Like you have to pick a few nodes from every subtree. Like let's say from this subtree, if you're solving, you need to pick some nodes such that the nodes that you have picked, the digit must not repeat. Okay. Like let's say you cannot take these three nodes. Like from this subtree, you cannot take all of these three nodes because the 2 is repeating here. Okay. But what you can take is you can take 23 and 5. This is allowed. So in this case, the score of the subset is 28. Like the sum of these two values. So whatever nodes you are taking in a subtree, the score is their sum. Okay. But the thing is that you cannot take two nodes which have a common digit. So here, since these two had a common digit, you cannot take them um, together. So you cannot take like all of these three. That is not possible. So either you can take 5 and 2, or you can take 5 and 23. So definitely you will take 5 and 23 because that will give you the higher value, right? So for this subtree, the answer is 28, right? Then for this subtree, what is the answer? In this subtree, you can just take all of them because they have all different digits. So 4 plus 7 plus 5, which is 16, right? Then in this subtree, you can, there's only one index, so you can take it. So the answer is 2. And for the entire tree, what is the answer? For the entire tree, definitely you will take a 1. Like you will take a 1 because it is the only single one there. Like there is no one otherwise. So you will take this one. Then you will take a 23. You will take a 4. You will take a 7. I think that's it. So the answer is 23 plus 4 plus 7 plus 1, which is 35. All right. So yeah, you have to just, like, what they are asking you to do is simply um, provide them the sum of answers to all the nodes, like the answer of this node, answer of this node, answer of this node. So sum of answers, I mean, this node means the subtree rooted at this node. Okay. So you have to find out the answers, the sum of answers for all subtrees. Okay. So how do we actually do this? Um, so okay, guys, just think about this. Like, okay, let us um, try one thing, that since we want to solve for all subtrees, right? Like we want to solve for this subtree, for this subtree, for this subtree, for this subtree, and so on. So let us just try to figure out that if we have the nodes of some subtree, then what can I do? Okay, like let's say this subtree is there. So in this subtree, the nodes are what? The nodes are 23, 25, and sorry, 23, 5, and 2. 23, 5, and 2. Okay, right? So in this case, what is the maximum score that we can get? So we will solve this somehow. Then we will solve for this subtree. Then we will solve for this subtree independently, right? So basically, the final TC of this would be n into the time complexity of to solve this. Like to solve this subproblem, that what is the answer for this? So let's say we take x time to solve this, then the final TC would be n into x, because we would have to solve for n subtrees, right? So how do we solve for a single subtree? Let's think about that. So first of all, the constraints are pretty low in this case. Like the constraints of n are up to just 500, right? So we can try to be a bit brute forcey, right? So okay, let's say we have this array 23, 5 and 2, right? And we have to find out the answer. So again, guys, this is also pretty similar to knapsack. Why? Because at each point you can either take or you can not take. You can either take or you can not take, right? And also, like, unlike knapsack, so here the value is just 23. Like if you take 23, then in your score you will get 23 added. So in this case the value is 23. But what about the weight? Like what is the weight? Here the weight is not conventionally weight. Like here we don't have actually knapsack. Like this is not exact same as knapsack. It is quite similar though. Like in knapsack what we have is we have total weight, and we can like carry a total weight of w at most. Okay. But here the constraint is that we can only carry one digit at most one time, at most once. We can only carry certain digit at most once. Like if we carry this 2 and 3, that means, like, basically we have 10 slots with ourselves. Like we have a bag, let's say we have a bag which has 10 slots: 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So if we take the 23, then the slots of 2 and 3 are full. Okay, so we cannot take any other 2 and any other 3. So this is how our knapsack looks like. Okay, so basically we have a bag which has 10 slots only, and we can take any number if that slot or those slots has not been occupied. So here let's say we had 35 or something. So if we are taken 23, we cannot take 35 because the 3 has been taken already, right? So whether or not we can take actually depends on what we have in the bag. Like the observation here is whether or not we can take at some point depends on what is in our bag, right? So basically if I have already 2 and 3 in my bag, then I cannot take 35, right? So definitely my answer depends on what I already have in my bag. So I can just try to store that information. Like if I do something like knapsack right here, then like in knapsack what we used to have w as our one of our states, where w was the remaining weight in my knapsack. But because in that case whether or not we can take the item depends on whether or not its weight was less than equal to our knapsack's weight, remaining weight, right? Like if in a knapsack 5 weight was there remaining, and the item was having weight of 6, then we could not take this item. So in that case we took the state of w, because our decision depends on the current weight that we have. So in this case our decision depends on, like, not a decision, but whether or not we are allowed to take the current element depends on already what we have in our bag. From these 10 digits, what do we have? Like these 2 and 3 we already have, so we cannot take 35. So That's what it depends on. So we can just take that as a state. Like just take what do we have currently as a state. Okay. So basically, what I'll do is I'll store a binary number for each, like for a state. Like, see, if I want to show that I have 2 and 3, I have taken 2 and 3, and the other ones I don't have, like I haven't taken, then I will store this binary number right here, like 0000001100. So this is a binary number, and the zeroth bit, one's bit, two's bit, three's bit, 4, 5, and so on. So here, as you can see, only the 2 and 3 bits are set, like they are 1, because I have these elements in my bag already, and the other ones are 0. So this is called bit masking. Like you are just storing your information in form of bits, right? So you can just store this as a mask. Like this is called mask technically. This is called mask. And mask means like what is your current state. Like mask basically means that this binary number is what right now, essentially, right? So what we can just store is like dp of I comma j. Like let's say we have recursive dp right here, or let's do iterative this time. Okay, if we do iterative dp this time, so dp of ij means the maximum value until ith index if our bag has j. Okay, and what does it mean by our bag has j? So see, let's say that j is equal to 7. Let's say, okay, 7. So 7 in binary is 111, and rest are zeros, right? So if j is 7, then that means that our bag has 0, 1, and 2. So these three are filled. So dp of I comma 7, dp of I comma 7 simply means that what is the maximum value that we can get until the ith index if our bag has the elements 0, 1, and 2, right? So if this is our state, then how do we transition? Like let's say, so now like we just have two options basically. If we are at dp of ij, let's say, if we are at some point, like basically if we are at dp of ij, okay, then we can actually either take a of I plus 1, either we can take or we can not take, but we can only take this a of I plus 1 if and only if the digits that this one has are free in our bag. Like if this is 35 and in this j the 2 to the power 3 bit is 1, that means we actually cannot take this a of I plus 1. So only the one option is that not take a of I plus 1, right? But let's say, so we'll check that, right? We'll just check that, and if we have the option of taking, then we will just update. We will update dp of I plus 1 times. Okay, now what is the new mask? What is the new mask? That means after taking a of I plus 1, what elements in our bag are filled? So dp of I plus 1 comma j or mask of a of I plus 1. So what does this mean? This mask of a I plus 1 is just that which digits are there in this a of I plus 1. Like let's say if a of I plus 1 is 35, okay, then the mask of a of I plus 1 will be just 0, 0, 0, 1, 0, 1, and then 0, 0, 0, 0. So 2 to the power 3th bit and 2 to the power 5th bit will be 1. So what we can simply do, if j doesn't have 3 and 5 set, then we can update this dp of I plus 1 comma j or mask of ai plus 1. And what I'm doing bitwise or. So bitwise or means that if a bit is set in this one or a bit is set in this one, then it will be set. Like basically it will take all of the bits which are 1 in this and all which are 1 in this, and it will make them 1. Like this bitwise or symbol is pretty clear, right? So if something I had previously, or if it is in the current state, then it will be in my bag. That's what it means. So dp of I plus 1 comma j or mask of a of I plus 1, I'll just update it. Like I'll set it to, like I'll try to maximize it with dp of I plus, I mean dp of ij plus a of I plus 1. Right. So essentially we have taken this a of I plus 1, and the maximum value would be the maximum value of ij plus a of I plus 1. Right. So you can just solve like this. So the transition is this. Like basically dp of I plus 1 comma j or mask of a I plus 1 equals to dp of ij plus a of I plus 1. And yeah, also this is when you take, like this is one option that you take a of I plus 1. And if you don't take, then just dp of I plus 1 comma j is equal to like dp of I comma j, because your bag doesn't change and you don't get any new value. The only variables which you have already taken in dpij, only those will be included in this, right? So that is how you can solve for a particular array. Like for this particular array, let's say 23 35 comma 2. Okay, so 23 35 and 2, right? So initially only our dp of 0 comma 0. Okay, let's say we have one indexing right here, so 1 2 and 3. So initially only our dp of 0 comma 0 will be equal to 0, because if we don't take anything, then every slot is empty. So at every point it is 0 0 0 0, right? And then what we can do is we can, okay, we iterate from right to left, left to right, and we can either take or not take this. So my dp of 1 comma basically 2 to the power 2 plus 2 to the power 3, what is it, 12, right? Like basically zeros, 0 0 1 1 and 6 zeros. This will get updated to 23, right? And if I don't take, then dp1 comma 0 will remain 0, right? And similarly we can just transition for all the dp values. And finally our answer is just the maximum value from dp n comma j. Like any j we can take, and that is the maximum value. I mean we can take any j, and whatever is the maximum value of dp n comma j, that is our answer, right? Because it is not compulsory that we have to take all of the digits. Like we can take any of them and just maximize our answer. Like in this case, in our maximal answer, like what is our maximal answer, we can take 35 and 2, right? So we'll get 37 as our answer. So in this case we have taken the digits 2 3 and 5. So the bit mask, which was 0 0 1 1 0 1 and then 0 0 0 0, this bit mask will store the highest answer. So basically our answer for a certain array will be the maximum value over all j for dp of n comma j. N comma j means like we have to consider the entire array, right? So the final index we will see, and all the values we will see from that. So that is our final answer for a particular subtree. And we have found this out in O of, like, see, what was our dp? Our dp of I comma j is, like, I is the index right here and j is the bit mask. So the bit mask has 10 bits, right? So it can be up to 2 to the power 10, right? So The bit mask has size 2 to the power 10, and the number of indices is just n. So n into 2 to the power 10. Okay. So this is for one subtree, and for all subtrees, like the final answer would just be in O of n into this thing, n into 2 to the power 10, because this is for one subtree, right? And for n subtrees that we have, we will take this much time, right? So that's the final answer. And like the main idea here was that the dp of ij, you will store that what is the maximum value until the ith index if you can take, like if you have taken only the jth bits, only the mask j, if your bag currently has j bits. I mean, yeah, if your bag has j, then from a of I plus 1, like you can take a of I plus 1 if its digits do not collide with what is there in j, right? And you can transition from that. All right. So is it clear, guys? Satvik is asking, why didn't I add 5? Okay, 1, 23, 4, 7, and 5. My bad. I can add 5 also. So the final answer is whatever it is, 23 plus 4, 27, 35, 40. Right. Pratham, I'll discuss that at the end of this PCD. Before that, do you all have some doubt? Just ask me if you all have any doubts. Okay, I'll just show the code, and meanwhile you can ask the doubts if you have. So the code is right here. Yeah, so in my this is my main function, go to subtree sum. Before that, I'll go to my dfs function. So my dfs function just makes subtree. Like basically my find answer takes in the indices, like it takes in the array, and then it just find out the answer for that, right? And this dfs function just calls this find ans for all subtrees. Okay, so the dfs function has, let's say, int v as a parameter, that the current v. Okay, so we will just make a vector that which uh, which nodes are there in v's subtree. Okay, and initially only v is there. Then I will do a dfs on all of its childs. So for auto x in adjacent of v, I just did a dfs on x, and it returned the subtree of x. Like that's what I'm returning right here, subtree of v. So when I'm doing dfs on x, it will return all of the vertices which are in subtree of x. So I'm just storing it in a vector, and I'll just add up all of these elements, all the elements from this vector into my subtree vector. So that's how I will get the subtree vector of this, and I will call the find answer on this subtree. So this find answer will just find my answer and will increment the, like since we want a total answer, right? The sum of all the answers. So it will increment the global variable called ans. I have a variable ans right here, and this will increment that. This function will just increment that global variable for this particular subtree, right? And how does this particular function work? So first of all, we have this n, and we make a dp of n plus 1 comma 1024, and we basically like make it one indexed. This subtree is initially 0 indexed, but I make it one indexed, so that I can store dp of 0 comma 0 as 0. So dp of 0 comma 0 means that if we have not taken anything, then our bag has nothing, and the value is 0, and all the other values are L long minimum, like minus infinity. Then what I'll do is, for int I equal to 1, I less than equal to 1, I plus plus, I'll find out the mask of val's subtree of I. Like whatever is the value of the current node, I'll get its mask. And what mask means is that what digits are there in its decimal representation. Like what digits are there in this value. So this mask function will return that, and it will return -1 if there are multiple digits. Like if in some number, let's say we have 22 or something. If we have 22 as a number, then definitely we cannot take it because it has 2 repeated twice, so we cannot take that. So if this mask is -1, that means it has multiple digits. Like I have defined this function like this. It will return -1 if it has multiple digits of the same type, right? So if mask is -1, then continue. And yeah, I am doing this dp of I comma j is equal to dp of I minus 1 comma j. Like if we don't take, then what is it? dp of I plus 1 comma j is equal to dp of I comma j, right? Or essentially dp of I comma j equals to dp of I minus 1 comma j for all j. So I just set this entire vector to this vector, right? That makes sense. So for all j, I am setting dp of ij to dp of I minus 1 j. That is if I don't take currently, right? And if I take, like I am looping over j, right? So if I take, then dp of I comma j or mask equal to like dp of I minus 1 comma j plus the value of the current element, right? And we can only do this if this j and mask is not equal to, like, is equal to 0. I mean, j and mask means what? J means that till now what we have taken, and mask is that now the current element has um which digits. So if their and operator is 0, that means there is no common digit, so we can take it. And if it is not equal to 0, that means there are some digits which are common, so we continue, like we don't take it, right? And also we have to ensure that this I minus 1 comma j is not equal to L long min. Like it is possible to get the exact submask j. We have to ensure that as well. So if dp of I minus 1 comma j is not equal to L long min, then we'll do this, right? And finally the answer is um, star max element of this dp of n. Like dp of n is a vector, right? So dp of n is a vector because dp is a vector of vector. So dp of n is a vector. So in that vector, whatever is the maximum element, that is the answer. So we will add that up in our ans variable, and we'll do that if it is not equal to L long min. And like actually it will not be equal to L long min. Like I just did, if all of the elements are equal to this thing, then I won't do it. But actually we'll have at least 1 0, right? The dp of n comma 0 will be 0, right? So we don't need this. We just need ans plus equals to star max element. All right. And finally we just call, like we just take the input. I mean, I just, like I have made this global variable called vals. So I just initialize it using this vals vector right here. And also I make the adjacent array. I have this parent array. From that I make the adjacent array by doing adjacent of parent of I dot pushback I for all I equal to 1 to n. And then I just do a dfs from 0. So that dfs from 0 will call all subtrees, and they will find all of the answers, and it will get added up in my ans variable. And finally I'll just print the answer modulo 10 to the power 9 plus 7. Like here it was given to us that we had to return the answer modulo 10 to the power 9 plus 7. So we return that. All right. Okay. So is it clear, everyone? Just tell me. Any doubts if you have, then just let me know. Hi guys, if you have any doubts, then just let me know. Okay, I'm assuming that I you don't have any doubts. All right. So now I'll just answer some general doubts that you guys have asked. So Pratham asking that Prady give me some tips to solve problems till D. I'm stuck till C. I'm stuck from C. That is, can you solve only till C or you can solve till D? I mean, can you solve till C or not? Assuming that cannot solve even C, like you are stuck only up to A and B, then I would just recommend you to, like, if your target is lead code, okay, like lead code and CF are pretty two different things. Then if you target lead code, then you should do many standard problems, like the DSA problems that you have, right? The standard DSA problems that you have, you should do them. All right, and you should do them according to what topic is your weak. Like if your DP is weak, then you should solve DP problems more. Like today, if you notice, this problem 2 or problem B was like a typical knapsack problem, but just that they just replaced the knapsack with some stocks, right? So if you knew DP very well, then you could easily do this problem. And yeah, even this last problem was also knapsack, but it was bit masking plus knapsack. So if you know bit masking knapsack, then you could do this. All right. So basically, just practice problems, and if you don't know some theory, then do some theory, right? And for CF, like if you want to grow rating on CF, then it is a different thing. Then, um, sorry, I think you should just practice problems. Like practice problems according to your rating on CF. Like if you are comfortable in solving problems from rating, let's say 1400 up to 1400, if you're comfortable, then try solving 1500. Like if you are having difficulty in solving 1500, then only solve 1500. If you can easily solve all of them, then don't solve them, right? That's my entire advice, that just do practice. That is the only thing that I can advise. Like that's what I have done. I am master right now on code forces, so I have solved at least like 1,000 problems or so, something like. Yeah, I have solved like 145 problems of all time. So that's what it takes to become a master, right? So yeah, just practice. And if you have like some difficulties in solving, then just look at the tutorial, or any solutions that you might have, right? So yeah, we can end this right now, and I think we will see you later. I hope to see you all later, and bye everyone. Thanks for joining. Okay, bye guys.